So welcome to the afternoon session. Our first speaker is Dr. Rohit. Vaish. He is now at University of Technology, Delhi. He is PhD in IIT and after a couple of postdocs joined IIT Delhi. He works on the interface of machine learning and economics. And I guess today's topic is a good example of that.
Thank you so much, Professor Burkar. Thank you. Thank you all for being here. I know this is the final day of a very intense program and post lunch, so we need some extra energy to be up. So I really appreciate you being here, and many thanks to the organizers, Sandeep and the rest of the team. It's been a real pleasure and privilege for me to be part of this program and interacting with many of you. It's been a fun sort of outing for me. All right, so I will be talking about a problem in the area of fair division, which very roughly is an area at the intersection of theoretical computer science and algorithms and economics and political science. Okay, so you can see sort of as an outward looking area of computer science that applies to problems in social sciences. Fair division very roughly translates to the following problem. You are given a bunch of resources, okay, and you are given a bunch of people who you want to give these resources to. Okay, and these people have certain preferences over these resources. Now your goal is to allocate these resources among these people in a way that is provably or mathematically fair. Okay, so we are going to write down some precise definitions of what it means to be fair, and then try to understand when can we develop fair solutions, when can we algorithmically find them. Okay, so that's sort of the one-line story of what's coming up. If you're somewhat familiar with this area, let me just tell you upfront that there are two kind of twists in this work that you don't see in the standard fair division literature. One is that we are going to talk about objects called chores, which are undesirable objects or tasks. And the other twist is that we are going to talk about a scheduling problem, which is going to model some constraints in the standard fair division model. Okay, so there are the two sort of unusual things that you will hopefully see in the slides to come. Okay, what I'm going to talk about is based on joint work with a bunch of excellent collaborators. Sarfaraz is a PhD student at IIT Bombay. Yatharth is a former undergrad from IIT Delhi. He is now working in the industry. And a bunch of wonderful faculty colleagues, so Raghuvansh from TIFR and Rohit and Swaprabha from IIT Bombay. All right. So just to, because I know that there's a lot of students and you like to see applications before seeing all the heavy math. So I thought I'll show you some pictures and applications and some motivating scenarios for why do we care about this problem. Okay. So like I said, we are going to talk about fair division, which deals with allocating resources to agents in a manner that is fair with respect to their preferences. And questions like these arise in a bunch of natural settings. For example, you can imagine that you are dividing an inheritance among a bunch of siblings or stakeholders, right? Now they can value different items or resources in the inheritance differently, and yet you want to divide the inheritance in a way that is perceived as fair by every single stakeholder, okay? Likewise, you can imagine that, say you are Ashoka University, and you want to allocate seats in courses at Ashoka, but you don't want to give all the seats in the best courses to the CS students. You also want to include the economics students. You also want to include the philosophy students and so on, right? Everyone should have sort of a fair chance at getting these star courses. And similarly, you can imagine that you might want to allocate scarce medical resources like vaccines or PPE kits fairly among the population, right? You want to be fair across age groups. You want to be fair across regions, whatnot. Okay, these are very natural questions that arise very immediately in a bunch of real life scenarios. I have chosen these three examples upfront because all of them, in certain sense, pertain to resources which are desirable, right? Because you want the more and more of these resources. These are typically called goods because you have a positive value for these resources. Okay. However, fair division is not just meaningful for allocating goods. It's also very useful for allocating undesirable resources, also known as chores, right? For example, you have a bunch of dishes that have to be cleaned up, right? Someone has to do it, right? And you don't want one person to do all the household chores. You want to sort of distribute them in an equal manner, in sort of an equitable manner, right? You could think of scheduling some tasks that arrive over time, right? These are tasks that have to be done, and you want to distribute them in a fair way. So that's another example. And yet another example could be allocating carbon emission responsibilities among countries, right? So it shouldn't be that the developed countries sort of impose the burden of sort of climate change on the developing countries. It should be equitably borne by all the countries. I think it's a very relevant fair division problem that we are facing as we speak. Okay, so this talk is going to focus on this lower row of resources. We are going to deal with resources that no one likes, but they have to be allocated fairly. Okay. Yeah, fundamentally, just the definition of what is fair is going to differ, and that translates to very different kind of algorithms for both. Yeah, so I'll point that out when we get to the model. Okay, but yeah, it's not just a sign change. It's more than, it's a conceptually different model. Okay, all right. And specifically, I'm going to focus on this scheduling style applications in this talk, but that's not to say that they are the only interesting ones. All of these are very well studied models within fair division, and I encourage you to check out various surveys and books written on the topic, or speak to me during the breaks. Okay. Okay. So just to give you a very cartoon picture of the model that we are going to consider, again, I'm going to keep this talk light on notation because I know it's a post-lunch session. People like to see pictures. So we'll mostly be dealing with pictures. Occasionally, some subscripts will pop out, but hopefully manageable. So here's the setting that we are going to talk about. You have a bunch of jobs or tasks that arrive over time. Okay, and these are represented as intervals. Every interval has a fixed start time, a fixed end time. Okay, and you have to finish that task within the assigned interval. Okay. Now you want to assign these intervals among agents. Okay, but the key assumption in our model is that agents cannot multitask. Okay, which means that at any given point of time, any agent can perform at most one of these tasks. They cannot do two or more such tasks at the same time. Okay, so that's going to be a very important assumption for us going forward. All right. Okay. Now, these are known as conflict constraints, right? And they are very naturally captured in a graph form, where you can imagine a graph whose vertices denote these intervals and whose edges denote overlaps between the intervals. Okay, so I have 4 intervals here, A, B, C, and D. You see those vertices over here. And I have an edge, say, between A and C, because their corresponding intervals overlap. So I throw in this edge here. But I don't have an edge between A and D because they don't overlap. So this is an edgeless pair. Okay, yes? Yes. Exactly. But for my purpose, I'm going to be happy with just this information. You're absolutely right. Yeah. Okay. Right. So we are going to capture these pairwise conflicts via the means of something called a conflict graph. Okay. And one term that is often helpful to remember is interval graphs, which is any graph that emerges as the conflict graph of a bunch of intervals. Okay. So you give me an instance of intervals that start and end at some point. Any graph that you realize, that class of graphs is called the interval graphs. Okay, yeah. I'll come to that. I'm just describing the graphical representation. I'll bring in the agents in just a second. Yeah. All right. Okay. So let me be a little bit more precise about the model. So we have little m many indivisible or discrete chores. What that means is that you cannot fractionally allocate the chores. Okay, so any chore or any task or any such interval must entirely go to one agent or the other. You cannot say, okay, half the time this job is done by person 1, half the time it's done by person 2. That's not allowed. Okay, and we have a bunch of specifically we have little n many agents. Okay, and we want to assign these chores among these agents. Now, because these are chores, right? These are undesirable objects. So we'll imagine that the agents have non-positive or rather negative values for these items. Okay, so I'll say that any agent I has a value v sub I of c for a chore c, and that's going to be a non-positive number, a negative number, if you will. Okay, and throughout I'll assume, at least for the purpose of this presentation, that value for subsets of chores are additive, which says that if I give you a bunch of chores, a set of chores, then your value for that set is the sum of your values for the individual chores in that set. Okay, so your values add up. These are known as additive valuations. Okay, so once I tell you the value for individual chores, you can reconstruct the value for any subset. Okay, all right. I just want to point out that this is just an assumption I'm making for the purpose of this talk. Many of the results that I'll present, they actually go through for much broader classes of evaluations, but that's not a super important comment here. Okay. Any questions about the model so far? All right. Okay. So like I mentioned, this is going to be a fair division problem with constraints, right? Which means that some solutions will be feasible, others will not be feasible. So what does it mean for an allocation to be feasible? So again, remember our input is given by a bunch of intervals, right? A, B, C, and D here. And we are going to capture that input by means of a conflict graph like this. Now, let's say you have two agents, okay? So I could start by assigning, let's say, this chore B to the red agent. Why not? I can do that, right? Once I do that, then I can no longer assign A or C to the red agent, because remember, agents cannot multitask, right? So if you are doing a chore and it overlaps with others, then you cannot do any of those other chores. Okay, all right. However, I can happily assign chore C to a different green agent. That's allowed, right? So this is okay to do. But again, note that once I give chore C to green, I cannot give to it A or D, right? But again, I can give D to the red agent because there's no conflict between B and D. They are disjoint chores, so red can happily do them. What is important to note here is that sometimes I may have to leave stuff unassigned. Why? Because I have this triangle sitting here, and I only have two agents. So there's no way I can assign all three chores among these two agents without creating a conflict, right? So just by necessity, I have to sometimes leave stuff unassigned. Okay? All right. Okay. So this is so much for what, yes. Just for example, we'll talk about general number of agents, essentially. Yeah. Okay, so I've told you what kind of solutions are feasible, but I haven't told you what constitutes a fair solution, right? So let's talk about that. So one sort of quintessential notion of fairness is envyfreeness, which we have heard on this stage before a couple of days ago, right? Envyfreeness just says that, okay, suppose I have a bunch of items and you have a bunch of items, right? If I think that your bundle is better according to my values, then I would envy you, right? And you don't want to be in a situation where people envy each other. You want to have an allocation where no one envies anyone else, which is what you call an envy-free solution, right? Now, it's very easy to see that even with two agents, even if you have just one item, there's no way you can have an envy-free allocation. Why? Because we are dealing with chores here. Whoever has to do the chore would be unhappy, right? So the owner of the chore would be envious of the other person, right? So even in very simple settings, you cannot ensure perfect envy-freeness, which then motivates you to define some relaxations or approximations of envy-freeness. And there are a couple of suggestions in the literature which have really been of interest to the community in the last few years. One approximation of envy-freeness is called envy-freeness up to any chore, or EFX for short. And what it says is the following. Suppose I'm giving to agent I a bundle X sub I. Okay, so agent 1 gets X1, agent 2 gets X2, and so on. Now, this allocation or this schedule, I'm going to call it approximately fair in this sense, if no matter what pair of agents I and K I'm looking at, right, I should be able to eliminate I's envy for K by dropping some chore in I's bundle, right? In fact, that should be true for every chore, excuse me, okay? Because I'm looking at E of X. So no matter which chore I drop in I's bundle, I would no longer envy K, right? And so note that here, I'm not actually discarding any chore. This is only as a thought experiment, right? Agent I is telling itself the story that, hey, I might envy agent K, but no matter which chore I remove from my bundle, I don't envy the residual bundle of agent K with respect to my own. Okay, so that's the sort of imaginary approximation that we are making here. Okay, any questions about the EFX definition? All right. Okay. So the quantifier is very important. We are going to ask for removing NV by dropping every single individual chore. Okay. Greater than, because I want to prefer my bundle over yours. That's perfect envyfreeness. That's not achievable. Yeah. So that's why we are making this dropping the chore assumption. Yeah. Yeah. Exactly. Say it again. Yeah, I mean, the goal of defining these notions is that I want universal existence, right? So envyfreeness is very easy to violate. Like I said, two agents, one item. You can have conditions, exactly, yeah, but we still feel it's too strong, right? Under very, very simple scenarios, it's violated, so kind of. Absolutely, absolutely, yeah. In fact, there are results which say that in the unconstrained fair division problem, if your values are drawn from a distribution, IID 0, 1, then you can get envy-free solutions with high probability, right? But that model is unconstrained. We are in the constrained setting. Yeah. Okay, all right. So this is the EFX notion. It's fairly strong. One could imagine relaxing this notion by changing the quantifier. Okay, so instead of instead of asking to drop every single chore, I this time just ask that you should have some chore in your bundle Xi, which if you drop, you'll stop envying the other person. Okay, so the quantifier changes from for every to there exists. Everything else remains the same. Okay, so two notions, EFX and EF1. Okay. Now, note that in a sense, it is absolutely trivial to satisfy fairness. How? You don't allocate anything to anyone, right? You just leave everything unassigned. Everyone ends up with an empty bundle. No one envies anyone, right? So that's not a very satisfactory solution. You would want some sort of efficiency on top of your fairness solutions, right? So we are going to again define a couple of hopefully natural properties. One property that's going to play a big role in this talk is what we're going to call maximality, which just says that, okay, sometimes you have to leave stuff unassigned, right? We saw that in the previous example, that sometimes the chore has to be left unassigned. Maximality says that for any unassigned chore, you better have a good justification. How? Well, it should be the case that if I take any unassigned chore and think about assigning it to any agent, I should not be able to do it without creating a conflict, right? If that's the case, if any unallocated chore creates a conflict with any agent, then there is a reason to keep stuff unassigned, right? So this is sort of a justification that we can give. That's a very bare minimum efficiency requirement that one could imagine, right? That's what we're going to call maximality. Just pictorially, the schedule on the left, right? It has two agents, red and green. You see this one gray unallocated chore. Note that this schedule is maximal because you cannot give it to either red or green. However, in the right-hand side schedule, there is no reason for keeping this extreme gray chore unallocated because you can happily give it to red. So that's why this schedule is not maximal. Okay. All right. All right. So the second notion that I'm going to explore is a strengthening of maximality, because maximality, although it's natural, it does seem somewhat weak, right? So you could ask for something on top of maximality. In particular, you could say, okay, I want my schedule to be maximal, but I also want that this schedule should not be Pareto improved by any other maximal schedule, right? So Pareto improved just means that you sort of weakly improve all the agents and strictly improve one of the agents, okay, in terms of their values. So these are the two notions that we are going to be thinking of, okay, and that means that basically now at hand we have two fairness notions, EFX and EF1. EFX is stronger, and likewise we have two efficiency notions, Pareto optimal and maximal, and Pareto optimal is stronger. Okay, and our goal is to understand, okay, what combinations of fairness and efficiency are guaranteed to exist, right, and which ones are not. Yes. Yes. So Pareto optimal is maximal because it's asking for maximal and something, right? You could be maximal, but there could be another maximal schedule in which no agent is worse off and someone is better off. If such a schedule exists, why wouldn't you switch to it? It's an obvious improvement, right? I want to negate such obvious improvement, right? It's giving you an additional efficiency benchmark. Yeah, so I didn't give you how agents value those chores yet. So that's why you can't decide whether it's a Pareto improvement thing or not. We'll come to the value instances in just a second, right? Yeah. Sorry. Um, yes. Absolutely not. No, no. There could be many maximal solutions. Possibly. Yes. There can be many. Yeah. So I'm in no way claiming that these solutions are unique, right? So there can be multiple things that satisfy these definitions. But our goal is to check if there is a single schedule always, no matter what the preference is, right? That satisfies simultaneously one of the fairness guarantees and one of the efficiency guarantees, right? We want to get them together. Yeah? Okay. Okay. So, so this is the guiding question, right? And if you have to explore, okay, what combinations of fairness and efficiency are simultaneously achievable, it's good to be greedy and start from the strongest property combination, right? So the strongest property combination for us is EFX and Pareto optimal, right? Wouldn't it be nice if there always existed a schedule that satisfies both properties, right? Then we can just declare victory and go home, okay? All right. So unfortunately, this is going to be the start of a whole bunch of bad news that I'm going to pile up in the next few minutes, which is that there are instances where there is no EFX and even maximal schedule, right? So even EFX and the weaker efficiency notion is incompatible, which implies that EFX and the stronger efficiency notion of Pareto optimal is also incompatible, okay? So let me try to convince you why that is. So here is an instance, right? So I'm now going to think of instances purely in terms of the conflict graphs. It's a very simple instance, just 4 chores, and their conflicts are given by a path, okay? I'm going to imagine I have 2 agents here, and both agents have the same value. It's an identical valuations instance, okay? So once I convince you that this is the right counterexample, you should be impressed. Why? Because this is a very strong counterexample, right? It holds even for 2 agents, even for identical values, and even when the conflict graph is a path, right? So for negative results, this is a very strong observation, okay? So let's see why. Okay, so remember, we are looking for an EFX and maximal schedule if one exists, right? The first observation I want to make is that if you look at this extreme chore, the -4, this heavily negative chore, I claim that under any maximal schedule, someone should get it. It cannot be unassigned. Yes? Why? Well, suppose you don't assign this chore, right? Then let's say the red agent is getting the -1 chore next to it, then you can give the -4 to green, right? And if the -1 is not assigned to anyone, then you can still, without conflict, give it to any of the 2 agents, right? So no matter what you do, if you insist on maximality, -4 chore must be assigned, right? In fact, both of the extreme chores must be assigned, this one and that one, by the same argument. Yes? Okay. So let's say the -4 chore goes to the red agent, okay? Now, my other obligation in this example is EFX, which remember says that no matter which chore you drop from your bundle, you do not envy anyone else. If I'm the red agent, I already have a very heavily negative chore at hand, so I cannot possibly afford to take another chore, right? Because if you give me a -1, and if I hypothetically drop it, my value would still be -4, and I would continue to envy the other agent, right? So that's it for the red agent, right? It cannot get any more chores, right? Which means the rest of the chores must either go to the other agent or they should be left unassigned, okay? Now remember, I told you that the extreme chores must go to somebody, which means the left extreme must go to blue. If that happens, then the chore next to it must be not going to blue to avoid conflicts. And when that happens, that means that this chore here must go to blue, because we said that it definitely, red cannot get anything else. Right? So if you want EFX and maximal, you must have a configuration like this. However, there's still a problem here, which is that now you can happily give this middle chore to red, right? If you insist on maximality. However, that would go on to violate EFX, right? So there is no schedule in this example, which is simultaneously EFX and maximal. Okay, that's the QED. All right. Okay. So now we have observed the conflict between EFX and maximal on a very, very simple example, right? So the next natural question would be, well, sorry, there's a question. Two agents and two chores with different values without conflict would be, sorry, I lost the, two agents and two chores. No, then you can give one chore to every agent. So no matter what the values are, you can always drop your chore and not envy the other person, right? Because values are negative. So there you can get EFX, right? You do need more chores to get the counterexample going, but maybe I missed your question. Okay, you got it. Thanks. Okay. All right. Good. So moving on, right? So now EFX is too strong, right? We have to lower our fairness benchmark. So let's think about EF1 now. Okay. Can you get EF1 along with, say, Pareto optimal or maximal, right? Preferably Pareto optimal, because that's stronger. Unfortunately, it turns out that just like EFX and maximal, you cannot get EF1 and Pareto optimal. Again, the counterexample is for two agents, again on a path graph, and again for identical values. Okay, so this is the counterexample. Because I'm running short on time, let me not walk you through it, but please ask me about it during the coffee break. Okay, it's a fairly straightforward argument, but you can just look at this and try to think about it on your own. Okay, let me just skip through. So believe me, EF1 and Pareto optimal are incompatible for now. Okay, which only leaves you with EF1 and maximal. Okay, that's our last hope for getting a positive universal existence result. All right. Sorry? Because EFX is incompatible even with this weaker property, right? We just proved that. Yeah. Okay. Okay. So I want to take a very brief detour and talk about achieving EF1 in the unconstrained model, right? Where you don't have any conflict constraints, right? That's the standard fair division model. We know how to achieve EF1 in that model. So let me describe to you how you get EF1 there, and then we'll try to see if those ideas apply in the unconstrained model. Okay, so this is just going to be a very brief digression. So the way you get EF1 in the unconstrained model is by means of something called the round robin algorithm, which does exactly what the name suggests. It lines up the agents in a certain order, right? And it's an iterative algorithm. In each round, every agent on its turn gets to pick its favorite remaining item. Okay, so A1 goes first, picks something, goes to the end of the queue, then A2 comes in, picks whatever it likes best among what's there on the table, picks that, goes to the end of the queue, and so on. Okay, so this is how the algorithm works. And when there are no constraints in the unconstrained model, round robin is known to be EF1. Fairly simple sort of proof by picture argument. So remember, EF1 is a pairwise property. So let's fix a pair of agents, red and blue. Now there are two cases, whether red is ahead of blue or whether red is behind blue in the ordering. So let's say red is ahead of blue, and we are looking at red's envy towards blue. Okay. So when agents pick items, right, it could be that maybe in the last round, red ends up with an extra chore, whereas blue doesn't, right? The chores could be such that we just run out of them, okay, for all we know. Pick anything, pick any permutation. I'm saying all of those give you EF1, right? Okay, so here is one permutation. Under this case, I claim that red's envy towards blue is bounded in the EF1 sense. Why? Well, imagine if red hypothetically drops this chore C from its bundle. Then item for item, red likes its bundle better than that of blue, because in every round it gets to pick before blue, right? So both items are on the table and red chooses to pick the item that it did. Okay, And by additivity, it likes the whole bundle better than that of blue. Okay, so this is, at least in this case where red is ahead of blue, you have EF1. Similar argument works when red is behind blue, right? This time you compare the item that red takes in round k with what blue takes in round k plus 1, right? Because at that moment when it's red's turn, both of those items are on the table. Okay, so again, if red drops its last chore, then item for item it likes its own bundle better than blue, right? And if you add more stuff to blue's bundle, it's only going to make that bundle worse off, right? So again, you get EF1 in this case. Yeah, all right. So round robin gives you EF1 when there are no constraints on the items, right? I want to now try to tell you that round robin would fail when you bring in the constraints. Okay, so this algorithm from the unconstrained world, which is very nice, provably fair, does not work when you look at the constraint problem. Why is that? Again, two agents, path, identical values, you know the drill, right? So let's run round robin on this example. Let's say you have red agent picking first. Obviously, it would go for the 0 valued item, right? Because these are chores. Okay. Then it's blue's turn. Obviously, blue would go for the next best, which is -1. Okay. Now it's red's turn. Red would go for -2. And note that it's safe to pick -2. No conflicts so far, right? Okay. Now it's blue's turn, and something interesting happens, right? Blue would like to jump at -3, but it's in conflict with its previous chore, so it cannot pick -3. It has to settle for a much worse chore, which is -7 in this case. Because if it picks -3, then there's a conflict here, right? That's the whole sort of reason why you don't get to pick the chores you like, right? Okay, and just to sort of rub salt in the wounds, red is going to pick the -3 chore very happily, right? So is life. Okay, and then blue will again very reluctantly have to pick the remaining terrible chore, which is -8, right? So what is happening is that once blue sort of misses its turn, right, its envy towards red is going to build up. And after a couple of rounds, the envy is so much that it exceeds the EF1 threshold, right? So suppose blue picks -8, then even if blue drops this -8 chore from its bundle, still it envies the red agent, right? So that's why it's in violation of EF1. Okay, all right. So this is just to sort of give you a sense of why standard algorithms from the unconstrained literature do not extend to the constrained world. There's a whole bunch of other examples we have in the paper where other algorithms of EF1 also fail, but this is just to give you a glimpse. All right. Okay. So so this is again looking very grim, right? The only sort of technique that we knew to find EF1 from the unconstrained world seems to fail in the constrained world. So what can we do? So I just have a couple of results to share on that front. The first result is that when you have two agents, okay, and when your conflict graph is a path graph, then we can prove that there always exists an EF1 and maximal schedule. Okay, obviously you can't use round robin, you have to do something else, and I'll show you what to do. But this is our first main result. Just a few footnotes to this result. So like I said before, although for this talk we are assuming additivity, this particular result extends to a very broad class of valuations called monotone valuation. Okay, I'm not going to define those, but just want to let you know that the result is much more general. Also, this result is not just an existential result. It comes with an efficient algorithm, with a polynomial time algorithm for finding such an allocation. And also, this technique extends to beyond path graphs. So if you have a general interval graph, right, remember that's the general class of graphs you get from interval instances, then you can get something weaker than EF1, which we call EF2, which says that, okay, instead of dropping some chore, you drop some pair of chores from your bundle. Okay, so it's weaker than EF1, but it gives you a guarantee for more general class of graphs. Okay, so that's result number one. You might say that two agents is very restrictive. I want something that applies to any number of agents, right? So we have, again, some partial observations on that front. So if you have an arbitrary n number of agents, as long as their preferences are identical, right? As long as they value the chores in the same way, and as long as the conflict graph is a path, we can again show the existence of an EF1 and maximal schedule. Okay. However, unlike the previous result, which came with a polytime algorithm, this time this is a largely non-algorithmic result. Okay, this is basically an existence result. I'll clarify why it's largely non-algorithmic in just a few minutes when I get to that point. Okay, but these are the two main results that I want to report. Are the statements clear to everyone? Any questions about that? So in the remaining few minutes, I'll just give you high-level proof idea of how we go about proving these results. Yeah, so we don't have a structure independent result yet, because even so, I do want to emphasize that, paths are still interesting, because all the counterexamples I gave you, they were all for paths, right? So many of the known techniques, they fail even when the graph is a path. So I believe the path is somewhat non-trivial still, right? But yes, it would be wonderful to have a result for general graphs. And I do point out in my open problems towards the end. Yeah, no, so yeah, I don't have a graph independent result. I think that's a very interesting question. Yeah. Okay. Okay, so let me just spend a few minutes on each of these results. So the first result is for two agents, a path graph, and the objective is finding an EF1 and maximal schedule. And the proof is going to use a kind of a color switching technique that hopefully, if anyone is looking into graphs and coloring problems, hopefully you can use it in your own work also. Okay, how does it work? So here's my input, right? This is my path graph. I want to come up with an EF1 and maximal schedule, right? Note that the agents can value these chores in any which way. You have no control over that, right? I'm not assuming identical values here. Your value could be very different from my value, okay? Anyway, so the first step of the algorithm is a very natural thing that one might try, which is to alternately color the chores. So red, blue, red, blue, red, blue, right? Why not? This is certainly a maximal schedule. It might be a terribly unfair schedule because people might envy others, right? I have not asked about their values in coming up with this schedule, so there might be a lot of envy in this, but it's maximal. So it's a starting point. I'm going to imagine a color flipped version of this schedule where I color it blue, red, blue, red, blue, red. So I basically exchange the bundles of the two agents, right? Okay. And what I'm going to do now is think of this schedule as my starting point, think of this color flipped version as my ending point, and construct for you a bridge between the start and end point by means of a whole bunch of intermediate schedules, each of which is maximal. And hopefully at some point, you start to see EF1 emerging. Okay? Okay. So first of all, note that, say I'm the red agent under X1, right? I might envy the blue agent under X1. I might like blue's bundle a lot better than mine. That means that under X6, I get blue's bundle, so I definitely do not envy blue anymore, right? So I envy blue here. If I envy blue here, then I definitely don't envy blue here. So at some point, my envy should switch, right? And I'm going to exploit that switch. I'm going to make that switch gradual by constructing a whole bunch of intermediate schedules. Okay, how do we do it? So the way we do it is by making some local tweaks to the current schedule as follows. Look at the first two chores. I want to make this blue and I want to make this red, right? So let me at least do half of the job. I'll turn this into blue. So I've fixed that part of my solution, right? I leave the second chore unassigned and I do not touch the rest of the tail. I leave it as it is, right? Note that this is a maximal schedule because this gray chore, this unassigned chore cannot be given to red or blue, right? So I have changed this schedule a little bit, turned it into that, such that this part of my target is fixed and I'm maximal. Okay. Let me repeat that. So now I look at the next two chores. I fix this part of my solution to red because that's what I want eventually. I turn this unassigned and I leave the rest of the tail untouched. Okay, and I hope you can see where this is going, right? I'm going to make these tweaks incrementally going to the right, okay? And it's not too hard to see that eventually I end up with my target schedule. Everyone believes that? Okay, excellent. Okay, so what we have is a whole bunch of maximal schedules, and there is an NV switch at some point, right? Okay, now this is where I'm going to take a leap of faith. Okay, I'm going to ask you that, believe me, the point at which NV switches, right? The point at which you stop envying the other agent or start envying the other agent, depending on which direction you're going, is where you find the EF1 schedule. Okay, and the very rough hand wavy idea is that because I'm making very little tweaks to the bundle of agents, only one item given and only one item sort of taken away, that translates to this approximate envyfreeness guarantee. Okay, you can prove this formally. I'm not doing it here, but that's really the idea. Okay, okay. So by this switching method, I can identify an EF1 and maximal schedule. Note that this is a polytime algorithm, right? Could be anywhere. It could be x1, x2, x2 to x6. The switch could happen. Sorry? No. I mean, this is just, it's 6 because I've chosen only so many chores in my path. Your path could have a billion chores for all you know, right? So I don't know when the switch would happen, depends on the values, but it will happen. It's guaranteed to happen. Okay. So that's so much for the first result. Let me very, very quickly walk you through the second result, because I think it uses a very cool result from graph theory, which to my knowledge has not been applied to fair division before, and hopefully you'll find it of sort of independent interest. So this big result is called the cycle-plus-triangle theorem, and here's what it says. It says that imagine any graph. Okay, the conditions are that the edges of this graph can be partitioned into two things. One is a bunch of triangle edges, which is given by these bold edges. And the other is a Hamiltonian cycle, which is a cycle that touches every vertex exactly once. Yeah. Suppose you are looking at graphs whose edge set has this kind of structure. It's a disjoint union of triangles and Ham cycles. Then the theorem says that such a graph is 3-colorable, meaning you can color the vertices red, blue, and green, such that for any edge, its endpoints have different colors. Okay. So this is an existence result that is guaranteed by the cycle-plus-triangles theorem. Fun fact: this was a conjecture of Paul Erdős around late 80s, and it was established in early 90s by Fleischner and Stevens. Okay. Another fun fact is that this result is not specific to triangles. You can say, okay, I don't want triangles here. Let me think of 4-sized cliques, a K4, right? Then the theorem says the graph would be 4-colorable, right? So you replace this 3-click by a 4-click, you get 4-colorable. You get 5 clicks, you get 5-colorable, and so on. So it's true for any K bigger than or equal to 3, any K click bigger than or equal to 3. Okay, but I just need 3 for the thing I want to present. You can have more than 3 what? Yes, this is just an illustration. The graph can have n vertices, right? Yeah, it's a general thing. Yeah, I mean, this is just an example. Yeah, so this would be a k vertex graph where it's a click. So k click would be k colorable. Yeah, this condition has to be satisfied. So you have k click edges and a Ham cycle. Okay, so this is the big hammer we are going to use. How does that tell us anything about EF1 and maximal? Well, here's how. Remember, now my conditions are that I'm given an arbitrary number of agents, but they have identical values, right? So this chore is of value -9 to all the agents, right? This chore is of value -6 to all the agents, and so on. Okay, all right. So this is our path graph. Given this graph, I'm going to create a different graph where I can apply the cycle-plus-triangles theorem. How? Let's pluck out. So imagine we have 3 agents. Okay, yeah, I'll rush. Yeah, suppose we have 3 agents. Okay, Again, the argument goes for any number, but imagine 3 agents. Let's pluck out the 3 worst chores from this instance, which would be -9, -8, and -7. Okay, and let's create a triangle in between them as follows. Okay. Next, pluck out the next 3 worst chores, -6, -5, -4, put them in a triangle, and keep going. Okay, so this is how you proceed. Yeah, okay. Now you see the triangles coming up. I still need the Ham cycle part somewhere, and I'm going to use my path constraints to encode the Ham cycle, right? So first of all, I'll connect the chores at the extreme points of this path, so -9 and -2. So I'll put an edge in my new graph between those chores, yeah? And then I'll encode these conflict edges in the path, right? So I'll put an edge between -9 and -6, like so. Then -6 and -3, the neighbors in the path, like so, and keep going. Okay. So the block of 3 worst chores give me the triangle. The path gives me the Ham cycle. I'm insisting that you pluck out the worst chores. Oh, you're saying that? Oh, I see. So yes. I think your question is, can it be that the Ham cycle edges go within the same triangle? That can happen. I've cleverly chosen the example so that it doesn't happen. You can address the same cycle situation by adding gadgets. So it can be addressed, but it's just a detail, so I'm not going into that. Yeah, but we can talk about it offline if you like. Yeah. Okay. All right. So I have turned my path graph into a cycle plus triangles graph. Now I can apply that big theorem. This graph must be 3 colorable. So I can assign colors red, blue, and green, right? And let me copy this coloring given by the theorem into the path that I have. Okay, because this is suggesting an allocation among the agents, right? Red vertices go to red agent, blue go to blue, and so on. Okay. So observe that because this is a proper coloring, right? This is a feasible schedule. There are no conflicts. Also, this is a complete schedule, right? Everything is assigned, so it's maximal. What's not obvious is why this is EF1, right? But this is where our round robin intuition would come in, right? Note that each triangle on the left is encoding the 3 worst chores, right? So if you are one of the agents, you can drop your chore from that triangle, and then item for item, you like your own bundle better than that of the other agent. It's just an artifact of the fact that you have encoded them in blocks of worst chores. Yeah. So this is exactly the proof by round robin. Okay. So let me just conclude because I know I'm out of time. There's a whole bunch of open problems, especially for the students in the audience, in case you are interested in working on these topics. So one very obvious direction is that we would love to have algorithms, right? This cycle plus triangles theorem and its implication for 3 colorings, it's an existence result. We don't know of polynomial time ways of finding this 3 coloring, right? So it would be lovely to have polytime algorithms for EF1 and maximal for general number of agents, even on a path graph. One could also consider fairness notions beyond NV, right? So if you look up the literature on fair division, you'll see things like proportionality, maximum share, equitable, and so on. You could also consider goods instead of chores. Interestingly, whatever I explained to you for chores, most of those insights actually carry over to goods. But what would be really interesting is if your model has both goods and chores, right? It could be that maybe you think of some item as a good, and I think of it as a chore, right? I often cite the example of regrading requests in my courses. For students, they are goods. For me, it's a chore, but yeah. And finally, as Sandeep was alluding to, it would be very interesting to look at more general graphs, right? Beyond interval graphs, the problem is well defined for any graph in particular. Okay, so this is all I had to say. Thank you for your time, and I'm happy to take questions.